All right, this is baby real analysis, and the topic for this series is integration, and this will be video 2 for the integration series of the baby real analysis YouTube playlist. So this is video 2. So assuming you have seen the first video, we talked about Riemann integration, and I wrote down the definition. We say f is Riemann integrable if for all epsilon there exists a delta greater than 0, and I denote it as delta with the subscript epsilon to reinforce that this delta depends on epsilon. So there exists a delta so that if P with the dot over it means it's a tagged partition. So if P is any tagged partition with the norm being less than delta, then the absolute value of the difference of the Riemann sum S of Fp minus L is less than epsilon, where L is the integral, definite integral of a to b of f. All right, so that is the definition for Riemann integrable, and recall that the S of Fp is the Riemann sum. And then P is a partition where it's any tagged partition. So you slice up some subinterval or some interval that the function is defined on, and based on your choice for that, for the subintervals, you can find the length of the largest one, which is the norm. If that is less than delta, then the difference, absolute value of the difference of the Riemann sum for the function of with this partition minus this value L is less than epsilon. All right, so here's the theorem. The theorem is if f is Riemann integrable on AB and k is some real number, k times f is Riemann integrable, and further, the definite integral of AB of k times f is equal to k times the definite integral of AB of f. So the proof, so given epsilon, we know there exists a delta, so that if the norm of any tagged partition P is less than delta, then the absolute value of the difference of the Riemann sum of S of Fp minus the definite integral AB of f is less than epsilon. So we know that because we are assuming that f is Riemann integrable. So that's just based on knowing that f is Riemann integrable. So we wish to show, so WTS for wish to show, this is sort of like the aside from the proof. We wish to show that for all epsilon there exists a delta, so if the norm of any tagged partition is less than delta, then the Riemann sum of k times f with the tagged partition P minus k times the integral of AB of f is less than epsilon. That is what we wish to show, because we need to show that k times f is Riemann integrable, and further that it's equal to k times the definite integral of a to b of f. So what we're going to do is use the integrability of f to find the necessary delta. So notice that the Riemann sum of S of k times f of with the partition P is equal to summation from I equals 1 to n of k times f of ti times xi minus 1. And that's just what we know for what the Riemann sum is, and ti is any tag chosen from subinterval where the subintervals of the form xi minus 1 comma xi. So we can pull out the constant in front of the summation. So that's what's going down here, going from this line to here. And so then going from this line to that line, so that's basically k times our notation is S of Fp for that, and that's the Riemann sum involving just f. All right, so we basically said that we noticed that S of k f p is equal to k times the Riemann sum of S of fp. Also, the absolute value of the difference of the Riemann sum of k times f minus k times the integral of ab of f is less than epsilon if and only if when we just take out the constant k, so it's k times the Riemann sum of f minus k times the integral of a to b of f is less than epsilon. So that's if and only if, and then we can pull out the constant. So that's if and only if the absolute value of that constant k times this absolute value of the difference of the Riemann sum of f minus a to b of the integral of f is less than epsilon. Well, that's true if and only if we have this to be less than epsilon over the absolute value of k. So basically, we're going to use the integrability of f to pick our delta to be epsilon over the absolute value of k. So I guess this could be kind of like scratch work, but I did include it in the proof to find the necessary delta. So this was the process or the logic that went in to find the required delta. Namely, we're using delta equaling epsilon over the absolute value of k. So then if the norm of any tag partition is less than this delta, which delta is epsilon over the absolute value of k, then it follows that we have the absolute value of the Riemann sum of k times f minus k times the integral of a to b of f is less than the absolute value of k times epsilon over the absolute value of k, which is equal to epsilon. All right, so that is the proof. Some of this probably could have been written as scratch work, but I like to, maybe I just could have written it a little bit better. But the actual proof part would be like using all of this, and that would be the actual proof, whereas this stuff right here is kind of scratch work, or the thought process. So hopefully that makes sense. So the proposition, if f is unbounded on some interval a to b, then f is not Riemann integrable. So I did a proof by contradiction. So assume f is Riemann integrable. So since it's Riemann integrable, we can let epsilon be 1, because we know by definition, since it's Riemann integrable, we know that the absolute value of the Riemann sum of f minus the value L is less than epsilon for all epsilon. So let's let epsilon be 1. And so for that epsilon, find delta. So if the norm of any tag partition is less than delta, then that absolute value of the difference of the Riemann sum of S of fp minus L is less than epsilon equal to 1. So f is unbounded, so it's unbounded on at least one subinterval. So find the subinterval xi minus 1 comma xi in which f is unbounded. So we can choose a tag in the subinterval appropriately and make the absolute value of the function evaluated at this tag, so f absolute value of f of ti, to be as large as we want, which then consequently means that we can make the absolute value of f of ti times xi minus 1 as large as we want. And then consequently, that means we can make the Riemann sum of S of fp as large as we want. In particular, we can find it so that this tag that we chose produces a absolute value of the Riemann sum being greater than the absolute value of L plus 1. And then if that's true, then that's going to contradict our assumption of S of Fp minus L to be less than 1. All right, so it probably could have been written a little bit more formal, but that is proof by contradiction. We're using the fact that F is unbounded, so that since it's unbounded, we can choose our tag so that the absolute value of the F of Ti is as large as we want, to make it such that when we do the Riemann sum, it's as large as we want. And in particular, it's so large that the absolute value of that Riemann sum is greater than the absolute value of L plus 1, which would contradict our assumption of F being Riemann integrable. All right, so here's a theorem. If F and G are Riemann integral on the closed interval AB, then so is F plus G. In particular, the integral of AB of F plus G is equal to the integral of A to B of F plus the integral of A to B of G. All right, so we're going to prove this. Now, first I'll do a sketch and then do the actual proof. All right, so notice that when I do the Riemann sum of F plus G with any tag partition P, that's going to be equal to the summation from I equals 1 to n of parentheses F of Ti plus G of Ti, all of that times Xi minus Xi minus 1, just based on what the Riemann sum is for that. And then we can break this up, so it's the summation from I equals 1 to n of F of Ti times Xi minus 1 plus the summation from I equals 1 to n of G of Ti of Xi minus 1. And these two things are the Riemann sums, where the first one is the Riemann sum S of F, and then the second one is the Riemann sum S of G. All right, so we know that Riemann sum of F plus G is equal to the Riemann sum of F plus the Riemann sum of G. And so we need to, and we know that these Riemann sums is approximately the definite integral of F, and then the other one's approximately the definite integral of G, since we know these are Riemann integrable. And so this is dependent on how skinny the rectangles are. So again, so these are approximately these things because of the Riemann integrable of these two functions. And so that's going to be for the rectangles being sufficiently skinny. Or in other words, if the norm of the partition P is sufficiently small. So the question is, how small do I need it to be? And we need it to be small enough to make the Riemann sum of F minus, or to be Riemann sum of f of p to be less than epsilon over 2 of f, the integral of a b. Let's see. And the same thing for g. And we can do that because of the assumption that f and g are both each Riemann integrable. So now the actual proof. All right, so given epsilon, we know f and g are both each Riemann integrable. So we can find the delta and I'm calling it delta with subscript epsilon over 2. So find this delta. So if the norm of any tag partition is less than this delta, which I'm again calling delta subscript epsilon over 2, then we have the absolute value of s of f b, so the Riemann sum of f minus a to b of the integral of f to be less than epsilon over 2, and the same thing for g. All right, so that's based on our assumption that f and g are Riemann integrable. So find this delta that produces this. So then if the norm is less than this delta, then we have the absolute value of s of f plus g, so that's the Riemann sum of f plus g with partition p, minus a to b of f plus a to b of the integral of g. Well, that's equal to s of Riemann sum of f plus the Riemann sum of g. All right, because that's what we did earlier in the sketch. We showed that this is the same as, is equal to these two as a sum. All right, and then distributing the minus, so then that would be minus the definite integral of a to b of f minus the definite integral of a to b of g. By triangle inequality and rearranging the terms, we could say this is less than or equal to the absolute value of the Riemann sum of f minus the definite integral of a to b of f. And the same thing for g. And so we know each one of these is less than epsilon over 2. So this will be less than epsilon over 2 plus epsilon over 2, which gives us epsilon. And that's what we needed to show. All right, so the proof is complete. All right, so that's where I'll stop it for this video, and we'll go into more propositions or theorems the next video. involving these Riemann sums. And these definition of Riemann sum, I'm using Bartol's textbook, Intro to Real Analysis, 4th edition.